Well, hello back. Welcome to organic chemistry. We have finished up what is, I think for a lot of people, the most difficult unit, which was the quantitative chemistry unit, which is how we look at quantities or amounts of chemicals being used. And in order to do that, we need to know the masses of chemicals. We need to use our periodic table to determine molar masses. We need to understand the concept of a mole. We need to balance equations, and it's all numbers. It's all a calculator, and you can put your calculator away. All right, we are going to turn from quantitative chemistry to trying to understand the nature of chemicals themselves that we find in our day-to-day lives. Now, the chemicals we find in our day-to-day lives are largely organic compounds. Right. So when we talk about this unit here, which is chapters 3 and 4 in our textbook, I put it off until after quantitative because I wanted to spend some time trying to get our heads around how much chemicals we need quantity-wise to be able to do chemistry. Now I want to talk about, for the next probably 3 weeks or so, what is really the main form of chemistry on the planet, and that is organic chemistry. Now, when I see the word organic, I often think about what I might find in a grocery store in the organic section, but that's not what organic chemistry is at all. Right? Organic chemistry itself is a branch of chemistry that looks at largely compounds containing carbon. Right? And that's basically what organic chemistry is. Now, going back, I'd say 100 years or so, and for thousands of years before that, the chemistry on the world was broken down into organic and inorganic chemicals. Either it was an organic compound or it was an inorganic or not organic compound. Organic compounds were things that were believed to have come from living things and to be in living things: hair, skin, blood, food materials, potatoes, apples, and all the chemicals, vitamins that are in food, all organic compounds, right? So anything that is either in a living thing or produced by a living thing was what we called organic. And then chemists discovered that they could make a lot of compounds that were similar to the organic compounds of living things in the lab or in a factory, in a controlled environment that was not the natural world, and we had to redefine what this idea of organic chemistry is. Now, it turns out that organic chemistry is a huge part of chemistry, right? When we talk about who are organic chemists, just about everybody who's a chemist today is an organic chemist. Organic chemists have to deal with, let's just scoot down here for a minute, and we're talking about all the things in our lives that we basically come in contact with. So we're talking about our food, we're talking about natural and fibers like cotton and wool and hemp. We're talking about all different types of plant products, whether it's lumber, paper, or again, plant products that are in food, plant products that are used in pharmaceuticals, that are used in all kinds of different, let's just stick with the natural substances. And these are as traditional as we would go back traditionally to look at different types of compounds. It also includes a huge sector which we as Canadians would be interested in, which are petroleum products, because we've got such a huge petroleum sector in this country. So there's a whole bunch of natural parts of our organic world, and then this came along, right? The discovery of artificial chemicals that are organic, right? They are built like organic compounds, but they're not made by living things. Right? And I should say that they're made by humans, but they're not made in a natural environment. They're made in a controlled environment, like I said, a lab or a factory or some type of industrial place. And basically, we have learned, and billions and billions of dollars and hours of human brain power have gone into understanding chemical reactions that make organic compounds. Now, wherever you are right now, if you look around you, look down at your clothes, look at the desk or table that you're sitting at, or if you're lying in bed, look at your blankets, look at your pillow, look at your drapes over your windows. Everything that I've just talked about are organic compounds. Right? All of those things are organic compounds. It includes all the plastics, right? All the synthetic materials, synthetic fibers, Dacron, rayon, acetate, acrylic, polyester. It just goes on and on and on. I would say the clothes that you're wearing right now, if you're not wearing cotton, wool, or silk, you're wearing synthetic materials, synthetic fibers. And even, like I'm sitting here wearing a t-shirt right now doing this note, and I'd say it's probably 20% cotton or 30% cotton, and then 70% synthetic fibers. Right? So they make up a gigantic part of what we do and use and in our lives. Right? And that includes food. Right? It also includes, because there's a number of different synthetic food materials that are made, artificial sweeteners, and then we talk about the pharmaceutical industry and making medication for treating this, for treating that. Today we're looking for medications that are antiviral agents to try and help us with the situation that we're in. We're trying to develop chemicals that are synthetic to use for vaccines, to try and protect ourselves from this virus so we don't have to be home the way we are now. And it just goes on and on and on. This is just a massive, massive, massive part of chemistry. All right. So, that being said, what exactly is it? Well, like I said before, it's basically carbon chemistry. Now, what we know about most organic compounds, it happens when carbon atoms are bonded to other carbon atoms. Right? Carbon is bonded to carbon, and that carbon is bonded to a carbon, and that third carbon is bonded to another carbon. And we can have huge, long chains of carbon atoms that are bonded together. And the way they bond together, because they're non-metals, right, they bond together by sharing electrons. They bond together using covalent bonds, and those covalent bonds make them molecular compounds that are not ionic, right, which means they don't dissolve in water. Right? So you wash your PJs, you wash your shirt, wash your pants, and they don't dissolve in water, right? Obviously, right, because they're not ionic material, they're molecular compounds. And because they're molecular, right, the atoms are sharing electrons, they don't dissolve in water. Now, along these chains, we also have largely huge amounts of hydrogen. In living organisms, we also use the elements nitrogen and oxygen. And then within our own bodies, we also have a few other elements like sulfur and phosphorus. I would say the four main elements in organic compounds are CHON: carbon, hydrogen, oxygen, nitrogen. Right? They make up 99% of you. Right? So if you weigh 100 pounds, 99%, probably 99.9% of you is CHON: carbon, hydrogen, oxygen, and nitrogen, and you are largely all organic compounds. Right? So this is a huge part of our life. And like I said, this is where, if this is such a big part of our life in terms of materials, all the plastics in the world, all the synthetic materials, all the pharmaceuticals, if you take a vitamin C tablet, if you take an aspirin, if you take a Tylenol or an Advil, again, it just goes on and on and on. So it is a huge, huge branch of chemistry, which means for you, that's where the jobs are. Right? That's where the jobs are. So as we start to move through this unit, everything comes back to carbon. Now, think, well, if so much of our world is organic, what is the rest of the world? Well, there's a lot of inorganic or non-organic materials. Rocks don't contain much carbon, right? They're other elements. Water, H2O, right? Most of the air, oxygen, nitrogen, right? Those are not organic compounds. So, again, you think about what makes up the planet. Well, most of the planet is right here. That's not part of the living part of the world. that is the organic part of the world. So we have organic and inorganic or not organic. Okay? And we're going to focus for the next 3 weeks, like I said, on all of these things, right? Food, petroleum products, plastics and synthetic materials, pharmaceuticals, synthetic materials, right, on and on. Okay, so let's go down. If carbon is at the center of all of this, then we need to really understand the carbon atom well. Now, if carbon is 6 on the periodic table, number 6, which tells me that there are 6 protons in the nucleus, and it is 12 for a mass, which means it's got 6 protons and 6 neutrons, right? It's got mass is 12 on the periodic table. Then I already know about its nucleus. And then if it's got 6 protons here in the nucleus, that means it must have 6 electrons. And I know that its 6 electrons have to be, according to Bohr, Niels Bohr, 2 electrons in the first orbit, 4 electrons in the second orbit. Now, these first 2 electrons here really don't do anything, right? They're there, they're stable, they've got their own shell, they're filled, and everything is happy. The problem with carbon are these 4 electrons that are in the outer shell. The outer shell is not full. Now again, if I was going to draw it as a Lewis diagram, here's my Lewis diagram over here with those 4 electrons that are looking for partners. Right? Again, remember, carbon wants to have a full outer shell. And it's going to do that by sharing electrons, these 4, with other atoms. Now, if it can find 4 atoms that have got an electron to share, then it can share its electron with a neighboring electron. I can share this electron here with an atom that's beside it that's got an electron to share. Like, let's say a hydrogen atom. So there's a hydrogen here, and a hydrogen's got its 1 electron. Hydrogen can share its 1 electron with carbon. Carbon shares its 1 back, and then we end up with a pair of electrons here. That pair of electrons, again, if we remember back to chapter 1, back to grade 10 even, that pair of electrons is the covalent bond. Now, remember I said one of the things that happens is carbon joins onto other carbons, so as we move through our note here, we're going to see how carbon will bond with other carbons. Now, we and everything on this planet are carbon-based life forms. We have a carbon-based living world such that everything that's alive on this planet, right, everything from those giant, what are they calling them? Murderer hornets that I was reading about in the paper today, that are in British Columbia, that are, they're the size of, almost the size of your thumb, right, these huge hornets. And they're carbon-based because they're alive on this planet. And fish and birds and orangutans and palm trees and dandelion plants and anything that's alive on this planet is alive because it's based on the element carbon. So carbon is the backbone for all of organic chemistry. Right? Carbon is the backbone, for all of life. And again, remember, originally our definition for organic chemistry was chemistry of living things. Right? Now again, if I take a step sideways and say, what is organic farming? Organic farming is a technique of farming that says we're not going to spray pesticides on our produce. Right? And that way, people who are eating the food are not going to be affected by the chemicals that were put on those food materials while they're growing, right? But that's really got nothing to do with organic chemistry per se. You're going to see as we move through this that organic chemistry really just is a science unto itself based upon carbon. So why carbon? Well, number one, if I look at some of the things about carbon, number one is the fact that carbon has got its 4 valence electrons. Right, it's 4 outer shell electrons. 4 is kind of a hard number for an atom because remember, it wants an outer shell which is filled. If it has 1 outer shell electron, 1 valence electron, it'll kick it out if it can and become an ion, a positive ion. If it has 7 valence electrons, it will steal one from somewhere and become a negatively charged ion. But because it's got 4, to make the outer shell full, it either has to steal 4 from somewhere or give 4 away. And we know that that doesn't happen very often. It's a lot of work to either gain or lose 4. So most carbon atoms will opt to share electrons instead of gaining or losing electrons. And again, they're nonmetals, so they will form covalent bonds with a number of different other nonmetal elements, like hydrogen, oxygen, and nitrogen. Now, because they have their 4 valence electrons, like we were just looking up here, these 4 valence electrons, let me get rid of this hydrogen from here, and that extra electron. Because of the 4 valence electrons here, it can form 4 covalent bonds. Now, let's just slide up. So if I look at the carbon here, this carbon, let's make this a bit bigger, this carbon atom right here has its 4 valence electrons. It has 1, oops, this is way too big. Let's make this smaller. I don't know that I can do that. It's got 4 electrons, so I'm going to switch to, it's got 1 electron here, 1 electron here, 1 electron here, 1 electron here. Those are the 4 electrons that carbon had in the first place. But then it's going to look around and find other atoms that will share electrons back. So if I look at this hydrogen here, with its 1 valence electron up there, the hydrogen can share its electron with carbon in exchange for carbon sharing 1 back with hydrogen. And the carbon becomes a little happier. It now has 5 electrons instead of 4 because it's sharing 1 with hydrogen. Hydrogen's pretty happy because it's got 2 and its outer shell is full. Hydrogen atom over here does the same thing. It takes its 1 electron and says to carbon, I will share with you if you will share yours back with me. And again, the hydrogen and the carbon make a covalent bond here, right? And I end up with a CH bond there also. Up here, the same thing. I end up with a CH bond. And over here, the carbon is actually bonded to another carbon. Now, notice that the carbon on this side had its 4 electrons for this carbon. On this side, it's sharing 1 with this carbon, which makes a CC, a carbon-carbon bond. And then the carbon on the left is going to share its other electrons with hydrogens to make carbon-hydrogen bonds. So what I now have is a bond between carbon and carbon, and then bonds between carbon and 3 hydrogens. Both carbons have 3 hydrogens each. What we often do when we're drawing molecules like this, instead of drawing Lewis dot diagrams the way we've been doing them, is we change every pair of bonding electrons with a dash. So each dash that you can see on this side, right, represents a pair of electrons, right? So this pair of electrons right here is this dash here. This dash here is this pair of electrons down here. So I can actually, instead of drawing a lot of dots, we can replace the dots with the dashes, where each dash represents a pair of electrons. So notice what that means on this side is I've got a hydrogen with a dash, which means the hydrogen is connected to 2 electrons. This hydrogen has a dash, so it's connected to 2 electrons. So those 2 hydrogens, 3 hydrogens, are all happy because they all have a dash. And the carbon in the center here is pretty happy because it has 2 electrons on top here, 2 electrons on this side, 2 electrons on this side, 2 electrons on this side. And that carbon is happy because it's got 8 electrons surrounding it in its valence space. And that carbon atom is happy. The same thing with the carbon atom on the right here. It's sharing its 4 electrons with the 4 surrounding atoms, 3 H's and a carbon, which makes this carbon on the right very happy also because it now has 8 valence electrons. and each hydrogen around it has its 2 valence electrons. Now, when we were talking covalent bonds earlier in the course, we talked about the fact that it's possible for some atoms to share more than one pair of electrons with its neighbor. So if I look at the carbon that I've got here, this carbon has its 4 electrons. Again, I'm just going to color them in black here. 1, 2, 3, 4. Those are carbon's 4 electrons. And it's chosen to take one of the 4 to share with a hydrogen down here to make a CH. And it's taken an electron here to share with hydrogen to make a CH. So it's used 2 of its electrons there, and it has the other 2 that it says to the carbon beside it, I need to share 2 electrons, but I need 2 back. So this carbon puts 2 electrons out. The carbon on the left puts 2 electrons out also. And ultimately what we end up with is 2 pairs of electrons in this space here, right? Or 2 bonds, or a double bond, right? I've got 1 pair of electrons here and 1 pair of electrons here. So when I look at what that looks like in terms of the dashes that we were talking about before, I can see I've got carbon bonded to 2 hydrogens using 2 of the carbon's electrons. And then carbon's taking its other 2 electrons, one of them to form a dash and the other one to form a second dash with the neighboring carbon. So I end up with 2 pairs of electrons, or 4 electrons in there between carbons, 2 from the carbon on the right, 2 electrons from the carbon on the left, right, which makes 2 bonds, because every shared pair is a bond. And then this carbon on the left is taking its 2 other electrons to bond with hydrogens. Lastly, it's possible, and again we saw this with nitrogen. Nitrogen forms N2. When nitrogen forms N2, it forms a nitrogen which forms a triple bond with a neighboring nitrogen, and it leaves 2 remaining electrons that don't end up being bonded with anything. Right? Because remember, nitrogen is 7 on the periodic table, which means it has 2 plus 5. Right? If nitrogen has 5 valence electrons, it takes 2 of its valence electrons and leaves them together here, and it takes the other 3 and puts them on this side. And the neighboring nitrogen has its 5, 2 electrons that stay together here, and the 3 that it wants to share with the neighboring nitrogen, and each nitrogen's contributing 3 electrons, which means I end up with 6 electrons, or 3 pairs, which means 3 bonds. And I end up with nitrogen and a triple bond between the nitrogens. These electrons that are outside on this side, and the electrons on this side are called non-bonding electrons because they're not involved in any bonding. And these are the bonding electrons here. There's 3 pairs, and they make up 3 bonds to make that triple bond. Carbon can do the same thing. Carbon has 4 valence electrons. We already know that. It's going to take 3 of the valence electrons over here, 1, 2, 3 in this space, 1, 2, 3 on this side. So I'm going to end up with 3 pairs, or 3 bonds between the carbons. And then carbon will take its 4th electron and use it to share over here with hydrogen. Let's get rid of some of my sloppy writing here. Oops. Cancel. I've got a triple bond in here because of the 3 electrons that I'm seeing over on the right, and then the 4th electron of carbons is going to be shared with hydrogen, the 4th one over here shared with hydrogen, so I end up with a carbon-hydrogen bond, a carbon-hydrogen bond, and then a carbon-carbon triple bond. So there's a lot of different ways that carbon can form bonds with neighboring carbons, right? But all of them involve the sharing of electrons. Now, the second thing that happens in biology is when carbon atoms form bonds with other ones to form long chains of carbon, 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 and they form long chains. And the bonds between a carbon and a carbon is a very strong bond. So again, it's the reason why we're as solid as we are, right? The carbon-carbon bonds in our bodies make for very stable and strong molecules that are hard to break apart. And then the last one is because carbon is so versatile with its 4 electrons, it can bond in a lot of different ways with other things and can form a lot of different types of molecules. So there's a huge array of different types of molecules that can be formed. And you're going to see as we get into this unit that we're going to be able to take a carbon and bond it to another carbon and bond it to another carbon, and then we end up with a molecule like this, where I've got this carbon on this end surrounded by 4 bonds, right? The 4 bonds are for the 4 electrons that carbon had, and it's sharing 1 electron with carbon and then 1 electron with 3 of each hydrogens. The carbon in the middle here has its 4 bonds. One's shared with carbon, one's shared with carbon, and the other 2 electrons are shared with hydrogens to make CH covalent bonds. And then on this end, I've got the same thing as I had on this end. A carbon which is sharing its 1 electron with carbon, and then 3 electrons with hydrogen to form this molecule here, which if you were barbecuing today, this is propane, right, that we use for our gas barbecues. Right, so this is propane. And if we look at something even bigger, this molecule here, right, all those carbons joined together, but again, notice that each of the carbons doesn't have 4 bonds there. So what usually happens in organic chemistry is we end up with molecules that we're going to realize are hydrocarbons. They contain hydrogen and carbon, and each carbon has to have its 4 bonds. So whereas most of the central carbons in this chain are sharing 2 electrons with 2 carbons, right? This carbon right here is sharing an electron with this carbon, an electron with this carbon, an electron with hydrogen down here, and an electron with hydrogen up here. Okay, and those 4 bonds, 4 electrons, just carry on. So we end up with these huge chains. Again, if you go to the gas station and put gasoline in your car, this is what you're putting in your car right here. Right? This molecule is called octane, right? Octa, 8. Oh, octopus, 8. Right? So this is 8 carbons long. 1, 2, 3, 4, 5, 6, 7, 8. That is octane. And with its 8 carbons, you can see what's happened is I've formed a long hydrocarbon chain. Now it turns out that if I erase a little bit of this, so let me get rid of all those greens that I just stuck on there, and let's get rid of my octane. Oops, let's get rid of my octane here. And I'm going to take one of these carbons off the end here, and I'm going to replace it with a hydrogen. So now there's only 7 carbons in the chain, right? But if I took this carbon off right here, this carbon off right here, and replaced it with another, so let's erase that hydrogen here, and I'm going to say, okay, now what am I going to do? Well, this carbon's in trouble because there's something not right. It's got 4 electrons. It has to have 4 bonds, and this carbon only has 1, 2, 3 at this point in time. So I'm going to put another carbon on here. And when I put that carbon on, now this carbon up here is happy because it's got its 4 bonds. This carbon at the bottom here needs to have 4 bonds. So I'm going to surround it by hydrogens. And now what I've got is a molecule which has 8 carbons again, but this isn't octane anymore, right? This is a totally different molecule. It doesn't burn like gasoline. It's a totally different thing altogether. It's kind of like this is an apple and the other one was an orange. It's a completely different thing, right? Apples and oranges are hugely different in their chemistry, just like these two. The 8 carbon I had a minute ago and the 8 carbon that I have here are completely different. This is probably somewhere in the world a really important molecule, and the one I had a minute ago, the octane, is a really important molecule in the world. So as organic chemists, we can start to change the way the carbon molecules are set up, the hydrocarbons are set up, and it gives us thousands and thousands of different possibilities. So the third thing that we were talking about in terms of why carbon is such an important molecule is because it lends itself to being able to produce so many different structures and shapes, right? And within your body alone, I don't know exactly, but I would guess that there's tens of thousands of organic compounds in your body, right? Tens of thousands of different organic compounds, if not hundreds of thousands of organic compounds in your body. Right, so as we get into organic chem here, just recognize you really need to be paying attention to the electrons around the carbons. Okay, remember, every line, every line here, every single line is a pair of electrons. One electron from carbon and one electron from the other atom that's bonded to the carbon. All right, so as we work through this, we really have to be watching to make sure that we've got the right number of bonds around every carbon, because they all have to have 4 bonds. Right? However that works out, again, notice that this carbon here has its 4 electrons, 3 on the right and 1 on the left. This carbon up here has got its 4 electrons, 2 on the right, and then the 2 for the 2 hydrogens, and then the carbon that I had originally. Again, let's get rid of some of my mess here. All right, if I look at this carbon here, I can see how its 4 electrons are bonded to 3 hydrogens and another carbon. All right, so that's going to be the gist of what we're going to be doing as we study organic chemistry over the next couple of weeks, 2 to 3 weeks. So I'm going to stop there for today. I'm going to leave you with the questions on page 96 in our textbook, questions 2 to 7. Again, notice that there's no calculator. We're not going to need a calculator, I think maybe even again in this whole course. We've spent maybe at the very end of the very last chapter, if we get that far, we might need to use our calculators again, but not for another month or so. So I was saying to you before, try and bear with what we're doing here. Stay on top of the math, practice the questions, do the math, get yourselves ready for the chapter 5 and 6 tests that we've just done, because they're math. And then once we get out of the math, we will be out of the math, which is where we are now. Okay, so if you are seeing this in the morning, we've got our ISU on environmental chemistry, chapter 8, is due next week on Tuesday, which is May the 12th, I believe. Tuesday, May the 12th. And on that day, you're going to hand in your ISU, so hopefully it's done. I know some of you have already submitted it. And you're going to write a test on that ISU